Today we're going to talk about trigonometry. And the main things in this video are going to be the sine rule and the cosine rule. But I thought we might as well start by talking about areas of triangles first, because a lot of the problems involving sine rule and cosine rule, as well as asking you to find the side or an angle of a given triangle, they usually also ask things about areas. So they are very closely related parts of the content. And I want to start by stressing the difference between right triangles and non-right triangles in this context of area. Well, first of all, you cannot just assume that a triangle is a right triangle because it looks like that, right? So that triangle, I am telling you that it is a right triangle. This one kind of looks like a right triangle as well, but we're not going to assume that because I didn't do it on purpose. It's just the way that the picture turned out. And because we are not supposed to assume things about triangles or any diagrams just because we think they look that way, right? So the information actually has to be there. Anyway, area of a triangle is something that we've all known for a very long time, that the area of a triangle is calculated as base times height divided by 2. And that's just because the triangle can be seen as half of a rectangle, right? It's not a formula that requires a lot of demonstration. But what you should definitely be aware of is that the concept of base and height is things that are perpendicular to each other, right? Because that is essential in the half of a rectangle thing. So this formula is clearly easier to use in right triangles because then the base and the height can just be taken as the two legs of the right triangle. But that's where the problems begin, because a common mistake that I see a lot is for people to look at this situation and interpret that the area of a rectangle, you should multiply two sides and then divide by 2. That is not true. It's not two sides. It's two sides in the special case where they are perpendicular because it's a right triangle, but base and height are not two sides of a triangle. So in other words, you cannot look at this triangle and say 10 times 3 divided by 2 is 15, so the area of this triangle is 15. That's wrong, because that formula is not talking about two sides, it's talking about base and height, which are two things that are perpendicular to each other. You can still talk about base and height in this triangle as well, of course, but then you have to know where the height is. And the thing is that it needs to be perpendicular to the side of the triangle that you are considering as a base. That's not enough information to calculate the area of the triangle given just the sides of the triangle, because you need more than this in order to calculate what the height is. If you also know the angle between the two sides that you have, say that it's an angle T, now you can use sines and cosines over here in order to figure out the height. And it turns out that that vertical segment is a times the sine of the angle T. So if you use that as a height to do base times height divided by 2, then you come up with this formula, which is the formula for the area of a triangle. This is also in the formula booklet. There is also something that you need to keep in mind about this formula. Just like in that one, you have to keep in mind that B and H have to be perpendicular to each other. Here you also have to keep in mind that the angle T that goes in the formula needs to be the angle that is between the two sides that you're using, okay? So it wouldn't work with A here, B here, but this angle or that angle, that's not going to work. It needs to be the angle that is between the two sides that you have. Now, a lot of times when I teach this formula, I get a certain reaction from some students, which is like, but why is this a formula? Can't I just draw a height every single time and calculate it and then use base times height divided by 2? Well, yes, you absolutely can, but that is all formulas, isn't it? We do it once with letters and then come up with a formula so that next time when we actually have numbers, we can just apply the formula instead of doing everything over and over again every single time, with the intention of just doing things faster. So if you want to slow down and deduce this whole thing over and over again every single time you need it, sure, feel free, but you're going to be wasting time during exams, and I just want you to be aware of that. But again, this is all formulas. This is not just this formula. For example, the sine rule. Say that you have two of these sides and two of these angles. Well, you have three of these things and you want to find out the fourth one, and then you're going to use the sine rule. But why do I need the sine rule? Why can't I just do it like this? Put a height here in the middle of the triangle. That gives me a right angle on that side and a right angle on this side. So by looking at the triangle on the left, I know that this height divided by b needs to be the sine of the angle A. And then, of course, h is going to be b times sine of A. On the other hand, if you do the same thing by looking at the triangle on the right side of the height that you put here, then you're going to get that the height divided by A is the sine of the angle B. Then if you rearrange these things, you're going to get the sine rule. So does that mean that the sine rule is absolutely useless? Because every single time you are in a situation that requires the use of the sine rule, you could just trace a height here instead and then look at this right triangle and that right triangle and do all of these things over again? Sure, in that sense, the sine rule is absolutely useless. But then again, that is all formulas. The reason why we use formulas is to speed things up so that we don't have to do this over and over again. We did this one time. Here's the demonstration that the sine rule is actually true. Now the next time we want to use it and do something with it, we're just going to use this. We're not going to go back to our sticks and stones and just work with this every single time. And now I'm going to do something that has absolutely nothing to do with triangles, just because I want to really stress this point that it's not that this formula is useless, it's all formulas are useless. So say you want to solve that quadratic equation. Do you actually need the quadratic formula? Well, of course not. You can just complete the squares if you want. I did that really fast in my head because it's not the point of this video. I do have another video where I teach you how to complete squares, so it's linked in the description. But after you do complete the squares, now you just have to solve that equation like the usual way, doing the same operation to both sides of the equation a lot of times as needed. There you go. I did not use the quadratic formula. Maybe I picked a bad example because a lot of people are going to say that this example should have been factored in the beginning instead of completing squares. And yeah, I do kind of agree with that point. It was a poorly chosen example, but just, choose stranger numbers there and you will not have the factoring technique available. But this technique is always available. And again, I did not use the quadratic formula. Why? Because this is exactly how we deduce the quadratic formula. We do this with letters A, B, and C instead of example numbers. I'm also not going to talk about it today because I have another video where I do exactly that. So does that mean that the quadratic formula is absolutely useless because you don't need it? You should do this every single time instead? Again, yeah, sure, of course, the quadratic formula is useless. Do this instead. How fast is that going to be? Okay, so I had really wanted to start this video by talking about formulas and the way that they're all useless but useful at the same time. But now that I got that out of the way, let's go back and actually talk about sine and cosine, because that is the point of the video, is to talk about trigonometry. So when I was doing the demonstration of the sine rule here, I said that the height was going to be b times sine of A, and I went through a previous step before that. I said that the sine of A is the opposite leg divided by the hypotenuse, and that therefore multiplying both sides of this equation by b, I got this one, which was the one that I actually wanted. But the thing is that I don't actually like defining sine and cosine like that, and I wanted to talk about that. I like it more when we go straight from the picture to this one, because I am thinking in terms of projection. I will take the b, which is the hypotenuse, and then project it over there away from the angle, and then that means multiplying by the sine of A. Don't worry, because I'm going to repeat all of these things, so if it sounded confusing, it's going to get better. Just keep watching. But the thing is that I really don't like to define the functions sine and cosine according to what they do in a right triangle, which is the thing about the opposite leg divided by the hypotenuse. That is right triangle stuff, because only right triangles even have sides that have those names. If if you want to distinguish both legs, like an opposite leg and an adjacent leg, they have to be opposite and adjacent to somebody, right? So it's always using this vocabulary when you are focusing on one of the angles, which in this case is this angle that I call T over there. So that leg is the one that is opposite to the angle T, and this one is adjacent to the angle T. And the hypotenuse is defined as the side of a right triangle that is opposite to a right angle. That is why there is no hypotenuse in triangles such as this one, because there is no right angle that the hypotenuse could be opposite to. But the same angle T could still be used in a different triangle, and its sine would be absolutely the same, and its cosine would also be absolutely the same, because the definitions of sine and cosine shouldn't refer to a triangle where this angle is currently drawn, because the sine and the cosine, they belong to the angle. They do not belong to a specific triangle. If you are talking about the same angle here, say T is 25 degrees and that's also 25 degrees, if it's the same angle, then the sine of that angle is also not changing, and the cosine of the angle is also not changing, because those are things that are properties of the angle, not of the triangle. So if you take as an example something easy like 30 degrees, that everybody has memorized that the sine of 30 degrees is a half, then in that right triangle it would be 5 over 10 is a half, sure. But in this one, 6 over 10 is a different number, but it's not because sine of 30 has changed. Sine of 30 is still a half in this triangle, but the thing is that you can't define sine of 30 as opposite leg divided by the hypotenuse. It's not the 30 that is wrong or the half. What's wrong is expecting the half to be 6 over 10, because this is not an opposite leg and this is not a hypotenuse, because this is not a right triangle. So anyway, I find it confusing to define sine and cosine by talking about right triangles, because that works very well while every student is only working with right triangles, but we know that eventually they're going to have to do non-right angle trigonometry, and that's going to be confusing. So instead, I like to work with the definition of sine and cosine in the unit circle. This is a circle of radius 1. The center is in the origin of the coordinate plane. The coordinates of each point in the circle are x and y. X, the horizontal coordinate, is going to be the cosine of the angle, and y, the vertical coordinate, is going to be the sine of the angle. But wait, what angle are we talking about? We're talking about this angle here. Okay, the angle in the unit circle starts at 0 here, and it's measured going up that way, counterclockwise. That is already better than you can do in right triangles, because the sum of the angles of a triangle needs to be 180, and the right triangle already has one that is 90, so the sum of the other two needs to be 90, which means that both of them have to be small. Both of them have to be angles that are less than 90 degrees, that is, acute angles. That means that they live in the first quadrant here, between 0 degrees and 90 degrees. But if we are working with the unit circle instead, there's nothing stopping us from going further into the obtuse angles over there in the second quadrant. And if you do that, you're going to realize that because this is the coordinate plane, the coordinates of the points work the same way that they've always done. In particular, the horizontal coordinate, the x, is positive all the way on the right side here, and it's negative on the left over there. So in this quadrant, the cosine is positive, and in this quadrant also the cosine is positive, but on that quadrant over there, the cosine is negative, and on this one here as well. So this angle here is an obtuse angle, like for example, it's 130 degrees, I don't know. So when I get to this point, a lot of times students are very surprised. They will say things like, wait, what? The cosine of an angle can be a negative number? But how is that possible if it's supposed to be the adjacent leg divided by the hypotenuse, and those are two measures of length which can't be negative? So you see, the surprise here is not that a function takes a negative value. This is normal for functions to take on negative values. The surprise is that it doesn't match something that they were previously thinking of as a definition, that the cosine is the adjacent leg divided by the hypotenuse. That's what I think makes it confusing. I don't like to look at that as a definition. I like to always say that the definition of cosine is in the unit circle. It's the x-coordinate of the point that corresponds to that angle. That is the cosine of an angle. The thing about what happens in the right triangle is an observation. It's a property of cosine. It's a special case of looking at cosines of a very particular set of angles, which are the acute angles, in a very particular situation, which is inside of a right triangle. And that's all true about the ratios, legs divided by other legs and whatnot. But that is not a definition, because if you think of that as a definition, then you're obviously going to be surprised by the existence of negative cosines and negative sines. And by the way, speaking of sines, which are vertical, of course, this is a coordinate plane, so the y-coordinate is positive on these quadrants up here, and it's negative on these quadrants down here. So there's even a whole quadrant where both the sine and the cosine of the angle are negative. So these things that I'm saying, I am very aware that this is an opinion, okay? This is my opinion. Other people will have different opinions, and it makes sense either way. It makes sense for you to think that the definition is in the right triangles and that this is an extension of that definition to other angles, or the other way around, that this is the definition and that is just a special case. Both of those things make sense logically. I'm just saying that personally I prefer this one. I find it less confusing. So the definition of sine and cosine that I'm going to be working with is the x-coordinate and the y-coordinate of a certain point. I think the coordinates of points are something that people are very familiar with. It's easy to look at. But I also like to think of it as something that is equivalent, which is, instead of looking at the coordinate, I am going to think of the segment, which is the radius of the circle. And here it has radius 1 because it's the unit circle. And I'm going to take that segment and I'm going to project it onto the horizontal axis to get cosine, right? If I want to get sine, I'm going to take the same segment and I'm going to project it onto the vertical axis. And this idea of projection, I think, is very powerful, so it's worth it for you to try to understand it. Here is the segment. I want to get it here on the horizontal axis. So I'm going to project it down here, I mean in a perpendicular way, of course, and whatever I get here is the cosine of t. Now if we're going to do the same thing, we're going to take this segment and project it onto the vertical side. Again, I want to make a projection that is perpendicular to the axis. Then whatever measure I get here is the sine of t. And this works perfectly well in the unit circle, where the segment that you're projecting always has length 1 because it's the radius of the unit circle. But if you were to scale this up and make a bigger circle with radius, I don't know, 3, that would work as well. So for example, if you have a right triangle with a hypotenuse is 5, it's no longer 1, and then you have this angle t here, you want to figure out the lengths of both legs. This is very easy, actually. This is just projection. You take this one and project it down to find 5 cosine of t, or you take the same thing and you project it to the vertical side to get 5 sine of t. Of course, you have to memorize which one is the cosine and which one is the sine, right? The one that is projecting on top of the angle is the cosine. The one that is projecting away from the angle is the sine. But that is consistent with what we were doing here, because in right triangles, all the angles are acute. So we are in the first quadrant. So the cosine will be measured here, which is where the angle is, and the sine will be measured on the other one, which is where the angle isn't? It's also consistent with what you knew before about sine being the opposite leg divided by the hypotenuse. It's just that now you can do things in one less step. If you have this diagram and you want to figure out the x, you don't have to go sine of t is equal to the opposite leg divided by the hypotenuse. Now multiply both sides of the equation by 5, and then you will get that x is equal to 5 times sine of t. You can just say, well, it's 5 times sine of t because it's a projection. The t is here, the 5 is there, so 5 sine of t. Again, just to speed things up, you can definitely do without it. I wouldn't though. I like projections. So anyway, in much the same spirit of, is this an extension of that, or is that a special case of that? There is another example of this kind of two ways to look at the same thing, which is that I wish I could teach the cosine rule before I teach Pythagoras. I would very much like to look at Pythagoras as a special case of the cosine rule, rather than looking at the cosine rule as an extension of Pythagoras. And the reason is pretty much the same, is to avoid confusion, because it is a very common mistake for students to look at this kind of exercise, just find x in this triangle, and then they try to use Pythagoras, like 8 squared is equal to 2 squared plus x squared, which doesn't make any sense. First of all, because 8 is not a hypotenuse, because it's not opposite to a right angle, but it happens. So I wish I could do that, treating Pythagoras as a special case of the cosine rule. I don't think I can though, and I'm about to show you why as I show you a demonstration of the cosine rule. Why is the cosine rule the way that it is? So here is the exact kind of situation that the cosine rule is good for. It's very similar to the example that I was just showing. You have two sides of a triangle, A and B. You want to find the third side, and you have one of the angles that I'm calling T here. Now, if you're finding it weird, the way that I drew B here is going to be clear in a moment why I did it this way instead of just putting the B here. It's because in the exact same way as I proved the area formula in the beginning of the video and the sine rule right after that, this one also starts with sketching a height here, making it into two right triangles, and I'm going to want to write down the length of one and the other, so it would be weird if the B was in the middle. The horizontal leg of the right triangle on the left is what? Well, let's do a projection of the side A over this angle T here and write A cosine T. We can do the same to the vertical leg as well, which is the height that I drew. It's going to be A sine of T because it's projecting away from the angle. So the other part of the horizontal side here is going to be the big one minus the left one, so B minus A cosine T. And hopefully now it's already obvious how I'm going to find the x length there. It's Pythagoras. This is the reason why I can't actually do this one before I do the other one. I need one to prove the other, so it would be circular reasoning if I tried to do it in a different order. But anyway, this is not quite ready, is it? We have to expand these squares. Careful not to mess up the special product on the other one there. Okay, it's this minus this squared. And now there are two terms here that need to be highlighted in order to look at them together. Because once again, the Pythagorean identity tells me that sine squared plus cosine squared is 1. So here I am using Pythagoras once again in the same demonstration. So there you go. The two red terms get together. Factor out the a squared. The sine squared plus cosine squared is 1, so that just becomes a squared. And then the rest is here. There is the cosine rule. Okay, so now let's do some exercises about sine rule and cosine rule. All of these exercises are always about, you know, some things about your triangle and you want to find out the other things. And one issue that you always have in this kind of exercise is choosing which one of the rules to use. cosine rule or sine rule. Now, in my opinion, the sine rule is always easier to use than the cosine rule. So whenever I have the two options available to me, I will always go with the sine rule because it's easier and faster. But the thing is that I don't always have both options. There are situations that necessarily require you to use the cosine rule. And the crucial observation that you have to make here in order to decide when you can or can't use one or the other is what kind of information you have and what kind of information you want. In this exercise, what you have is all three sides. So what you want must be an angle. Let's say you want that one. So putting that together, what you have with what you want is always going to be four things. Look here, 1, 2, 3, 4 things. And in the cosine rule as well, there's A, B, C, and then the angle C over there. So both of them require four things, three of which you know, and the fourth one is what you want. Now, it doesn't matter really what you have and what you want, but if this set of four things is three sides and one angle, like here, then it has to be the cosine rule. You can't use the sine rule instead, because look at what the sine rule uses. It's two sides and two angles. I don't have two angles in my problem. In fact, I don't even have one angle, but I do want one angle, so that counts. Has to be the cosine rule for that one. And I haven't mentioned this explicitly in the video yet, but this is always true. The capital letter of the angle and the lowercase letter of the side are always one opposite the other, okay? So if I'm going to use angle T here in the cosine rule, then the side that counts as the C in the formula needs to be the 5 because it's opposite to the T. So let's write it out. And I do realize that in the IB formula booklet, you also have a second version of the cosine rule typed out there, which is for exactly this kind of situation where you have all three sides and you want one of the angles. But that other version of the cosine rule is simply isolating the cosine in this expression. So at least for the purposes of the video, I think it's good if we do it this way. Because there is one thing that I want to mention in this sequence of steps that I'm about to go through, which is that it's perfectly fine right now to do 9 plus 49 is equal to 58, but you cannot now do 58 minus 42 is 16. This would be wrong, and it's a mistake that I see students make so often that it's even made me understand why the formula booklet has both versions. It's because they don't want you to have the opportunity to make this mistake. The mistake that I'm talking about clearly is order of operations. In this sentence, you have a subtraction and you have a product. Product comes before subtraction in the order of operations, so you cannot subtract 58 minus 42 before you multiply the 42 times the cosine of t, because product needs to come first. I know that everybody knows this, like rationally you know that product comes before subtraction, but I think that the reason that people make mistakes anyway, even though they know it, it's because there is something very weird here about saying, oh, you have to do that one first, but I don't know how to do it because I don't know the value of t, so I can't make this product now. And this is true, okay? This is an actual issue with calculating this now, but the conclusion can't be, there is a rule that I have to do that first, but I can't do it now because I don't know it, therefore I'm going to do the other one first. That can't be the conclusion, because doing the other one first is something that you know is wrong. The conclusion needs to be that you're going to do something else, right? And the something else that you're going to do should be to subtract 58 on both sides to get to this place here. And now you can divide both sides by negative 42. There you go. The cosine of t is 11 over 14. Of course, that number means absolutely nothing to me. But this would be a calculator problem, right? So the next step is to say that t is the cosine inverse of 11 over 14. So here's a different situation that can happen. Now I've switched it. I know the angle. I still know two of the sides, but now I don't know the third side, and that is what I want to find. Now, I would have made it into a slightly easier problem if I had kept the 7 here and said that I don't know the 5, because then that would be opposite to the angle that I know, and I could write out the cosine rule like that. But I chose to make it a little bit more difficult because the side that I want is not opposite to the angle that I have. So I still have to start with the side that is opposite to the angle I have. So that means that I have to start by writing 5 squared. And I still can't use sine rule in this situation because it's still involving 3 sides and only 1 angle. And in order to use sine rule, you need 2 angles. So the reason why it's going to make it more difficult in this way, it's because the x that I want to find ends up appearing in 2 parts of the cosine rule. It's here squared, but it's also there. And because I wanted to make this one into a problem without calculator, I chose one of the angles that we know the sine and cosine of. I chose pi over 4, whose cosine is the square root of 2 over 2. Now I can cancel this 2 with the 6. I'm going to have a 3 here. And now I've put everything to the same side because this is a quadratic equation and I want to use the quadratic formula. Okay, this looks very ugly. Bear with me for a second here. 9 times 2 is 18. 4 times 16 is 64. 18 plus 64 is 82. And I don't think that one is going to factor nicely into a third. It's just 2 times 41. But wait, there's a plus or minus, so do I have 2 answers? Well, no, not really. Sometimes you can, but not in this situation. 82 is more than 81, so the square root is more than 9, and this is not more than 9. So if you do this minus that, it becomes a negative number. Your x can't be a negative number, so it's actually just this one. Okay, so what about this kind of situation now? I have one angle, I want to find another one. So now there's 2 angles in the game, which means that I want to use the sine rule. Again, I'm picking an angle whose sine I know, but if it was a different angle, then it would be a calculator question and everything else is the same. But don't forget that in the sine rule as well, it needs to work with opposite pairs, okay? So the 5 needs to go with the pi over 4, and the 3 needs to go with the t right here. Let's put the square root of 2 over 2 here. Now dividing the fraction, this 2 is going to come up, making it into a 10. Now I guess I'm going to cross multiply. And if I actually wanted to know the value of the angle now concretely, I would need to use the calculator. But that doesn't mean that this kind of thing will only happen in calculator questions, okay? There are ways to phrase the question so that you don't need to go this far. So one thing that they do sometimes is to say, find the value of sine of t, so that you don't have to use a sine inverse. And then they will say things like, find it in the format a root b, where a is a rational number and b is an integer, which is exactly the same kind of thing that we found here. So this would be a equals 3 over 10 and b equals 2. But when they say something specific like find it in that format, that means that even if it is a paper 2 and you have your calculator with you, then you shouldn't use it, because they're not looking for an approximation of the number. They actually want you to go through the algebraic steps to get to it in this kind of format here. Another funny thing that can happen sometimes is if you don't have the side that is opposite to the angle that you're trying to find, how are you going to still use the sine rule in that kind of situation? Well, maybe you find the other angle first, right? This one that I called S here, even if they're not asking you for S, this is a strategy that you can use in order to get to T, which is what they're actually asking you for. So you say, well, I don't have the opposites to T, but I do have the 7 here, which is opposite to S. So I can find S by using the sine rule in these 2 pairs. And then after I have S and I always had this angle, then I can just make the 3 sides of the triangle add up to 180 and I'll have the T. Well, I guess that was it. Those were the things that I wanted to say about the sine rule and the cosine rule. If you still have any questions, feel free to leave them in the comments.